All right, welcome back to another lecture. We're going to cover section 3.3 in this video. This is all about confidence intervals and how they relate to hypothesis tests when we're trying to perform inference. And I thought that a good way to kind of approach this topic would be to talk about statistical and practical significance. So hypothesis tests are an important inferential tool, but they don't tell us the whole story. All a hypothesis test does is tell us if an effect or difference exists, but it doesn't really tell us anything about how large that effect is. So in inferential statistics, statistical significance shows that an effect exists in a study, while practical significance shows that the effect is large enough to be meaningful in the real world. Statistical significance is easy. Well, not easy, but it's clear when something is statistically significant, because all that means is that we have a small p-value, right? That our p-value is less than our level of significance. Practical significance is a little bit more slippery, but one of the ways that we can sort of get our heads around whether a result is practically significant is to estimate how large the difference is, okay? And we do that using confidence intervals. So sometimes a result can be statistically significant without really having a lot of practical significance. For example, let's say that we're testing p equals 0.25 against p greater than 0.25, and let's say that our sample evidence is that p hat is 0.26. Now, if our sample size is large enough, then we would reject the null hypothesis here in favor of the alternative, okay? Even though there's maybe only like a 1% difference between what we're observing and what the null hypothesis states, right? Now, depending on the context, that 1% difference might be important, maybe not. So in any case, right, we want to get a measurement for about how much of a difference we have between what the null hypothesis says and what was observed. And that's where confidence intervals come into play. So let's talk about confidence intervals. A confidence interval for an unknown parameter is a range of numbers that uses a sample statistic known as a point estimate to estimate the parameter with a certain level of confidence. The idea behind confidence intervals is that we want to estimate a parameter like the proportion p or the mean mu based on a sample statistic such as p hat in the case that we're estimating a proportion, or x bar in the case that we're estimating a mean. So the sample proportion p hat is a point estimate for p, and the sample mean x bar is a point estimate for mu. Now, different samples are going to result in different values for p hat and for x bar, and so we can't say with any degree of certainty that p is equal to whatever value we got for p hat, and same thing for x bar and mu. Instead, what we'll do is we'll report a range of values, and that's what we call a confidence interval in order to estimate a parameter. So for example, if we got a sample proportion of 25%, right, and we want to estimate what the population proportion is, we could not say that the population proportion is 25%. What we might say is that the population proportion is 25%, give or take 1%, right? And so our confidence interval would be 24% to 26%, right? So that's the idea here. Now, the tools that we used in the previous lecture from artofstat.com, those will come in handy for computing confidence intervals as well. The only difference is that we'll choose the confidence interval option instead of the significance test option when we go to compute a confidence interval. So with that in mind, let's just jump right in and compute some confidence intervals. Number one here says the drug Lipitor is meant to lower cholesterol levels. In a clinical trial of 500 patients who received 10 milligram doses of Lipitor daily, 45 reported a headache as a side effect. Part A asks us to compute a point estimate for the proportion of Lipitor users who will report a headache as a side effect. Now, the point estimate for a proportion is the sample proportion p hat, okay? And our sample proportion in this case would be, well, there were 500 patients and 45 of them said they had a headache, so it would be 45 out of 500, which is exactly equal to 9%. So there's our point estimate. Okay, now part B says construct and interpret a 90% confidence interval for the proportion of Lipitor users who will report a headache as a side effect. So for that, we need to open up the appropriate web app in artofstat.com. Later on in the notes, I have direct links to these things, so I'm going to go ahead and use that. I want to perform inference on a proportion, so I'm going to go to this link right here. And dismiss this. I mean, you can, of course, download the cell phone app, right, if you want, but I'm just going to do this from my computer, so I'm going to say dismiss. So in this example, our sample size was 500. And the number of patients who reported headache was 45. So that was the number of successes. And that's it. Notice that the type of inference here is already set to confidence interval, which is what we want. And we wanted a 90% confidence interval, so I'm just going to move this slider down to 90%. And we get our confidence interval. They graph it on a number line here, and then they also give it in interval notation here. So we would say a 90% confidence interval for the proportion of headaches is somewhere between 0.06895, so about 6%, to 0.1111, right? So to about 11%. You don't have to change any of this other information. You can just leave it as is. So this is our confidence interval. Let's write that down. So let's round to 3 decimal places here. So we'll go 0.069 to 0.111. Okay, so we have, we went to Art of Stat. We entered 45 for the number of successes and 500 for the sample size. And the confidence interval that we got was 0.069 to 0.111, approximately. Did I get that right? Yeah, 0.069 to 0.111. So there's our confidence interval. Now we were asked to interpret this interval. So the interpretation would be something like, we are 90% sure or certain or confident, maybe confident's the best word. We're 90% confident that the true population proportion of Lipitor users who will experience headache is somewhere between 0.069 and 0.111. You could state that differently, right? You could say we're 90% confident that between 6.9% and 11.1% of Lipitor users will experience headache as a side effect, right? That would be another way to state the same thing. Okay, let's do another one. Part C says, construct and interpret a 99% confidence interval for the proportion of Lipitor users who will report a headache as a side effect. So we're going to do the same thing, right? Art of stat. We're going to enter 45 for the number of successes, number of people who had a headache, 500 for the population size. But this time we're going to do a 99% confidence interval. So maybe I should have said on part B that we used a 90% confidence level. Okay, and here we'll do a 99% confidence level. Let's see what we get. Okay, so all I'm going to do is I'm going to take this slider that was at 90% from the previous part, and I'm going to slide it over to 99%. Okay, and again, right, the interval is shown here graphically, and then it's given numerically right here. It's also given numerically here in this chart, okay? Notice that they also give you the sample proportion, which they conveniently call the point estimate. But okay, so we would say that this is about 0.057 to 0.123. So 0.057 to 0.123. And again, our interpretation here would be similar, right? We would say we're 99% confident that the true population proportion of Lipitor users who will experience headache is somewhere between 0.057 and 0.123. I'm going to state that slightly differently, though. Okay, because we could also say it like this. We are 99% confident that somewhere between 5.7%, that 5.7% and 12.3% of Lipitor users will experience headache. Okay, so that's another way that you could give the interpretation. Now, a couple things that I think are worth pointing out. Notice that our sample proportion was 0.9, right? That was our point estimate for the true population proportion of Lipitor users who would experience a headache as a side effect. But we can't be at all certain that the population proportion is exactly equal to 0.09. What we can be sure of, we can be about 90% sure that the population proportion of Lipitor users who will report a headache as a side effect, right, is between 6.9% and 11.1%. We can be 90% sure of that. We can be 99% sure that it's somewhere between 5.7 and 12.3%. So notice that going from 90% confidence to 99% confidence, the width of our interval increased, right? And that makes sense because if we want to be more confident that our interval actually contains the true population proportion, then we need to cast a wider net, right? With that in mind, Part D asks us to, without using technology, construct and interpret a 100% confidence interval for the proportion of Lipitor users who will report a headache as a side effect. And if we want to be 100% sure that our interval contains the true population proportion, well, then we would just say that our interval would go from 0 to 1. In other words, we are 100% sure that the proportion is between 0 and 1. Okay, that doesn't really give us any useful information, but we can be 100% sure of it, right? So the more specific you want to be, the less precise you can be, right? The more confident you want to be, right, the less precise you're able to be about your estimates. And if we want to be perfectly confident, then we can't be precise at all, right? We just say, this is like saying, yeah, we're 100% sure that somewhere between 0% and 100% of people will experience a headache as a side effect, which just doesn't tell us anything useful. Okay, so part E asks, how certain are we of each of the following claims? First claim is that p hat equals 0.09. Well, we're 100% sure of that. We know that in our sample, 45 patients experienced headache and there were 500 patients. That comes out to exactly 0.09. So we're 100% sure that our sample proportion was 9%. Okay, but we are 0% sure that the population proportion is 9%, right? Do you see that subtle difference? Here we're looking at the sample proportion. We're 100% sure that it was 9%. That's what we observed. Okay, but here we have the population proportion. We don't know what that is. We're trying to estimate it, and we can't be at all certain that it's 9%. We can, however, be 99% certain that the population proportion is between 0.057 and 0.123, because that's what we got for our 99% confidence interval in part C. Okay, here's another set of follow-up questions about this confidence interval. It says, are the following claims possible, and if so, are they likely? So the first claim is that more than 10% of Lipitor users experience headache as a side effect. Yeah, I would say that's possible. In fact, not only is it possible, but it seems fairly likely, since 10% falls inside of this interval, and it also falls inside of this interval. So yeah, we would say this is both possible and likely, right? Seems fairly likely. Okay, the next claim is that more than 20% of Lipitor users experience headache as a side effect. Well, 20% is possible, but it's not very likely. The upper bound on our confidence interval here was 11.1%, and here it was 12.3%. 20% falls far beyond that upper limit, so that would be highly unlikely, right? That the true population proportion would actually be 20%. It's very unlikely. So this is possible, but not likely. And maybe I can give some justification. So let's go back to the previous one and add some justification so that when you're reviewing your notes, you know where this came from. It won't let me erase that little period right now, so I'll just make it a comma. This is both possible and likely because 10% is in the confidence interval. Whether you're looking at the 90% confidence interval or the 99% confidence interval, 10% is in both of them, whereas 20% is not, right? So 20% is possible, but not likely, because 20% falls outside our confidence intervals. Okay, and then finally, the last claim is that more than 110% of Lipitor users experience headache as a side effect. Well, this isn't even possible. Okay, it's not possible. So it's not likely to happen, of course, because it's not even possible in the first place. You can't have more than 100% of anything, right? More than 110% of like, what would that even mean? That's not even possible. Okay, let's do another one. So number 1 was an example of a confidence interval for the proportion. Let's do a confidence interval for the mean. This one says the NCAA reports that the mean number of hours spent per week coaching and recruiting by assistant football coaches is 70. A random sample of 50 assistant coaches showed the mean to be 67.86 hours with a standard deviation of 8.2 hours. Okay, so 67.86 hours, that's a little bit less than 70, right? So So maybe the NCAA isn't quite telling the truth or something. Well, we could construct a confidence interval to see, kind of whether 70 is within the realm of possibility given what we have observed in our sample, right? So that's what part A asks us to do. Construct and interpret a 95% confidence interval for the population mean. So to do that, let me open up the app for inference for the mean. So I'm going to click on that first link. And let's go enter data. Let's enter some summary statistics, okay? And we can give a name to this variable if we want. We can call it hours coaching. Our sample size was 50, right? They sampled 50 assistant coaches. The sample mean was 67.86. And the sample standard deviation was 8.2. And here under type of inference, we want a confidence interval, so we don't need to change that to significance test. We'll leave it confidence interval. And we want a 95% confidence interval, so this is already set up. Again, they're giving us the interval graphically and numerically, okay? So our confidence interval is 65.53 to 70.19. So we went to Art of Stat. We entered 67.86 for our sample mean. We entered 8.2 for our sample standard deviation, and we entered 50 for our sample size, okay? And then to get a 95% confidence interval, or rather, our 95% confidence interval was 65.53 to 70.19. Okay, so there's the confidence interval. Now we were asked to interpret this. So the interpretation would be something like, we are 95% confident that the true population mean number of hours that NCAA assistant coaches we're 95% confident that the true population mean number of hours that NCAA assistant coaches spend coaching each week is between 65.53 hours and 70.19 hours. Okay, let me try to write that again. Hours. Okay, so there's our interpretation. You could state that differently, right? You could say we're 95% confident that NCAA coaches spend somewhere between 65.53 hours and 70.19 hours coaching each week, right? Something like that. So part B now asks a follow-up question. Does your interval support the claim made by the NCAA? Well, the NCAA's claim is that assistant coaches spend 70 hours a week coaching. And 70 hours a week is in our confidence interval. So I think that our confidence interval substantiates, right? It supports the claim made by the NCAA. Our interval supports the claim made by the NCAA, because 70 is in the interval, right? It's in the confidence interval. Okay, similar set of questions now about this interval as in question 1. How certain are we of each of the following claims? First claim is that the sample mean is equal to 67.86 hours. Well, we're 100% certain of that, right? We know that in this particular sample of 50 assistant coaches, the sample mean was 67.86 hours. So we're 100% sure of that. We are 0% sure that the population mean is 67.86 hours, okay? Just because this particular sample of 50 coaches had a mean of 67.86 doesn't mean that the population mean of all assistant coaches will be 67.86. We can be 0% sure of that. However, we can be 95% sure that the population mean is somewhere between 65.53 and 70.19 hours, because that's what we got in our confidence interval. Okay, so let's look at these next claims and determine if they're possible, and if they are, whether they're likely. The first claim is that the mean number of weekly coaching hours is more than 70. That's possible. It's also somewhat likely that could be the case, because that falls within our interval. So yeah, that could be the case. It's possible and somewhat likely. Although it's also likely that the mean hours spent coaching is, between, let's say, 66 and 70, right? That would also be likely. But this one is possible and somewhat likely. Okay, next claim. The mean number of weekly coaching hours is more than 80. Okay, so that's possible, but not likely. Because 80 is outside our confidence interval. So it's possible, but not likely. And then finally, the mean number of weekly coaching hours is more than 170. Now, I have a sneaking suspicion based on the pattern of these questions that this is not possible. But to see why this is not possible, note that there are only 24 hours in a day, and there are only 7 days in a week. So if you're talking about the amount of time someone spends coaching, the maximum it could possibly be would be 25 times 7, right? Since that's the number of hours in a week. And 24 times 7 is 168. So we could say not possible, because 24 times 7 equals 168, right? There are only 168 hours in a week. So it's not possible that the weekly number of coaching hours is more than 170, because there are only 168 hours to work with to begin with, right? Okay. So that's how confidence intervals work. We've seen an example of constructing confidence intervals for proportions, and then another example constructing confidence intervals for means. Let's talk about how they relate to hypothesis tests, okay? So first of all, just as a summary of the hypothesis tests we've looked at so far, right? We're going to follow these steps, right? First, we determine the null and alternative hypotheses, and we could have two tilde left tilde right tilde tests in any case. Okay, then we gather the sample evidence, right? If we're testing a proportion, then we'll want to gather the sample proportion. If we're testing a mean, we'll want to write down what the sample mean is, so that we have some idea of what our sample evidence is indicating. Then we'll compute the p-value, and we'll use art of stat to do that. then we'll use the p-value to make a decision. If the p-value is less than alpha, we reject the null. If the p-value is not less than alpha, then we do not reject the null. And then finally, we'll write a conclusion about what our decision means for the alternative. Okay, if we decided to reject the null, then that means there's sufficient evidence to support the alternative. Okay, if we decided to not reject the null, then that means there's not sufficient evidence to support the alternative. And notice how all of the positive statements go together and all of the negative statements go together. If our p-value is less than alpha, then we do reject the null, and there is sufficient evidence to support the alternative. Whereas if the p-value is not less than alpha, then we do not reject the null, and so there's not sufficient evidence to support the alternative. It's always that way with hypothesis testing. There's never any mixing and matching. It is always the case that if the p-value is less than alpha, you reject the null, so there's sufficient evidence to support the alternative, and if the p-value is not less than alpha, you do not reject the null. Not sufficient evidence to support the alternative. Okay, now the results of this hypothesis test will tell us if the result we obtained in our study is statistically significant. In other words, it'll tell us if there's an effect or a change or a difference in our sample compared to the population. Now, if that's the case, if there is an effect, then we would like to measure how large the effect is, and that's where the confidence interval comes into play. So whether you're computing p-values or confidence intervals, you're going to use the appropriate app from artofstat.com. You could either just go to artofstat.com or and then find the appropriate tool, or you could use these links to get there directly. This one for the mean, this one for the proportion. Okay, and then you'll enter the data, right? Either summary statistics or raw data if you have raw data. And then under type of inference, if you want the p-value, you'll go to significance test. If you want a confidence interval, you'll go to confidence interval. Okay, one last thing to say before we look at some examples. The level of significance in a hypothesis test, alpha, is how sure we are that we're not rejecting a true null hypothesis. Okay, it's the cutoff value that we give for ourselves. And it's how comfortable we are with making a mistake, essentially, right? If we set alpha equal to 0.05, then we're saying we're okay with rejecting a true null hypothesis 5% of the time. Now you might say, why don't we set alpha to be 0? But the problem with that is the same as the problem with setting a confidence interval to 100%. The more confident we want to be that we're making the correct decision, the less accurate, the less precise we can be with our confidence intervals. And it's the same way with the hypothesis test. In fact, one thing that we should point out here is that the level of confidence and the level of significance are related to each other. They're complements of one another, okay? So a 5% level of confidence, right, alpha equals 0.05, corresponds to a 95% level of confidence, okay? A 10% level of significance corresponds to a 90% level of confidence. And in general, an alpha level of significance will correspond to a 1 minus alpha level of confidence. Okay, so if we wanted to have an alpha equals 0 level of significance, then we would have to have a 100% level of confidence, and that's not going to lead us to useful results. Okay. All right, so let's take a look at some examples. Number 3 here says, in 1966, support for the death penalty was at an all-time low, with around 46% in favor. In April 2021, a Pew Research poll asked 5,109 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 3,002 were either somewhat or strongly in favor. And now the question is, have people's feelings about the death penalty changed since 1966? We're asked to test at the 0.05 level of significance. Okay. Step 1 is to state our hypotheses. So first thing we should do is figure out whether we're testing a proportion or a mean. in this scenario, we're talking about whether people are in favor of the death penalty or opposed to it. So if you went around and you asked people, are you in favor of the death penalty? They're not going to give you a number, right? They're not going to say 17. They're going to say yes, or they're going to say no. And so that means that we have categorical data on our hands. We don't have the raw data, but the raw data would have been categorical when it was first collected. And so for categorical data, we're going to test the proportion, right? So we're testing a proportion. More specifically, we want to know if the proportion is the same as it was in 1996, in 1966. The proportion in 1966 was 46%. Okay, but we want to know if people's feelings have changed. Now, we're not necessarily interested in knowing if the proportion has increased or if it's decreased. We just want to know if it's different, right? We just want to know if it has changed. And so we're going to run this as a two-tailed test. Okay, step 2 is to collect our sample evidence. We'd like to know what the sample proportion is, p hat. Well, the number of people in favor was 3,002. The number of people surveyed was 5,109. So the sample proportion of people in favor of the death penalty would be 3,002 over 5019. And you can punch that into your calculator, but it comes out to about 0.598 approximately. Or in other words, about 59.8%. Okay, that seems like a big change to me. That seems like a very large difference. So it seems like people are much more strongly in favor of the death penalty now than they were in 1966. Okay. Step 3 of the hypothesis testing procedure is to get the p-value. So to get the p-value, we're going to go to art of stat, and we'll enter in the number of successes, 3,002, and the number of observations, 5,109, and then we'll get the p-value out of this. Let's see what we get. So, art of stat, for a proportion, we're going to use this second app. Okay, so we want to use the second app. We have the number of successes is 3,002, and our sample size was 5,109. The number of successes. Okay, we don't want a confidence interval just yet. We're looking for the p-value. To get the p-value, we have to enter the null hypothesis, right? Our null hypothesis was that 46% of people would be in favor, right? The null hypothesis is that the proportion of people in favor is the same as it was in 1966, which was 0.46. Okay, and we're going to run this as a two-sided test. So I think we're set there. Our p-value is tiny. Notice that the z-score here, our test statistic, is 18, right? That means that our observation is 18 standard deviations away from the mean if we assume that the null hypothesis is true. So if we assume that people's opinions haven't changed since 1966, there would have been pretty much a 0% chance of observing what we've observed in our sample, okay? So that's worth writing down. Okay, so our p-value is approximately 0. Sometimes sometimes when a p-value is that small, art of stat will say that the p-value was less than 0.0001, and that's just its way of saying that the p-value is so small that we don't even have enough digits to show you exactly how small it is. So it's really small. It's less than 0.0001. Okay. So step 4 is to make a decision. We compare a p-value to alpha. Alpha in this case was 0.05. 0.05. So we would say 0.0001 is less than 0.05, right? This is our p-value, or rather our p-value is even smaller than that, and this is alpha. So our p-value is less than alpha, so we reject H null. Since we're rejecting the null hypothesis, that means we have evidence to support the alternative. And that's what we would say in conclusion. There is sufficient evidence to conclude that people's feelings about the death penalty have changed. Okay, that's all the hypothesis test would allow us to say. It wouldn't allow us to say by how much it has changed, nor would it allow us to say in what direction it's changed, right? Because we just ran a two-tailed test, so all we know is that it's different. You could look at the sample proportion and you could say, okay, well, clearly it's bigger, right? Clearly, people are much more in favor of the death penalty now than they were in 1966. To get a handle on exactly how much the change has been, we can construct a confidence interval, which is what part B asks us to do. It says construct a 95% confidence interval. So we can do that real quick. Hopefully it doesn't kick us back out. It just kicked us out. So I'll have to do this again. 5109 and 3002. And this time we do want that 95% confidence interval, so we'll leave it there. So yeah, our confidence interval is 57.41 to 60.11%, or you could leave it as a decimal, 0.5741 to 0.6011. Okay, we went to art of stat. We put in 3002 for the number of successes and 5109 for the number of observations. And we constructed a 95% confidence interval, and we found it to be 0.5741 to 0.6011. Okay, so there's our confidence interval. Now some follow-up questions. By how much has the proportion changed since 1966? Well, in 1966, the proportion was 0.46. It was 46%. So in 1966, right, the proportion was 0.46. Now, it's somewhere between 57, let's stay consistent. Now it's somewhere between 0.5741 and 0.6011. So the proportion has changed by somewhere between well, let's see. 0.5741 minus 0.46 is 0.1141. So somewhere between 0.1141 and 0.6011 minus 0.46 is 0.1411. So the proportion has changed by somewhere between 11% and 14%. So that's, now the next question is, would you consider this to be a practically significant difference? The answer is yes, absolutely. So yes, this is a practically significant result. Okay, an 11% difference at minimum is very significant. That's very practically significant. Okay, so this was an example where we had statistical significance because our p-value is small, but we also had practical significance because at the very least, the proportion has changed by 11%. So that's a huge difference. Let's look at another example. It says, according to the American Time Use Survey, the typical American spends 67.8 minutes, about 1.58 hours, per day watching television. Do TikTok users spend less time per day, or less time each day watching television? A survey of 150 TikTok users resulted in a mean time watching television per day of 63.3 minutes with a standard deviation of 16.5 minutes. Part A asks us to determine if TikTok users spend less time watching television at the 0.01 level of significance. Okay. So this time, again, we want to run a hypothesis test. We've got to set up our hypotheses. And this time, we're going to be testing a mean, okay, rather than a proportion. We know this because if you took a survey and you asked people, how many minutes do you spend watching television each day? They're not going to say green, right? They're going to say something like, oh, I spend about 45 minutes watching television each day, or something like this, right? And so this is numerical data. And so we use the mean to test numerical data. We're going to say the null hypothesis is that the mean, right, that the average Joe, right, spends the same amount of, or rather the average TikTok user spends the same amount of time watching television as any other typical American, right? That their average time watching television is 67.8. The alternative that we want to test, an old habit. The alternative that we want to test is that the average is less, right? We want to know if TikTok users spend less time watching television than the average user, so that would be less than 67.8. The sample evidence that we would collect here would be the sample mean. We were told in our survey of 150 TikTok users, their sample mean was 63.3 minutes. Okay, that is less than 67.8 minutes. So maybe that is a statistically significant result. The only way to know for sure is to compute the p-values. That's what we'll do in step 3. We're going to once again go to Art of Stat. We'll have to enter the sample mean, the sample standard deviation, which we were told was 16.5, and the sample size. This was a survey of 150 TikTok users. So let's see what the p-value is. Okay, so I want to go to inference for the mean. I'm going to open up this app. I want to enter summary statistics. We can call this minutes watching television or something like that. Our sample size on this problem was 150 TikTok users. Okay, the sample mean was 63.3, and the sample standard deviation was 16.5. And let's get a p-value. So we're going to run a significance test. The null hypothesis is that mu would be equal to 67.8, right? The average for non-TikTok users. And we wanted to know if TikTok users spend less time watching television, so we'll use a less than. Okay, so we're running a left-tailed test. So it looks like the p-value here is 0.0005, so a pretty small p-value. Let's write that down. .0005. Okay, so we can make our decision. We compare our p-value to alpha. Alpha here was 0.01, but our p-value is still less than that, right? So once again, we reject the null hypothesis. Since we're rejecting the null, we have evidence to support the alternative. And that's what we would say in conclusion. There is sufficient evidence to conclude that TikTok users spend less time watching television than non-TikTok users. Again, this only tells us that there is a difference, there is a statistically significant difference, but it doesn't tell us how big that difference is. It might not be very substantial, right? Okay. It also doesn't tell us that TikTok users are virtuous people, right? Just because they're spending less time watching TV. First of all, it doesn't seem to be that much less. It's like a 4-minute difference, okay? Which isn't that substantial. But also, they're probably spending less time watching television because they're on TikTok instead, right? Scrolling through TikTok. So it's not necessarily that much better. But okay. Part B asks a follow-up question. What does the p-value mean in this scenario? Well, our p-value is 0.0005, right? What that means is, if we assume that the null hypothesis is true, then the probability of obtaining a sample mean of 63.3 is 0.0005. Okay? So, assuming that the null hypothesis is true, in other words, that mu equals 67.8, the probability of obtaining a sample with a sample mean x bar of 63.3 or less, right? Since this was a two-tailed test, right? So we would say 63.3 or less. Is 0.0005, right? In symbols, you could write it this way: probability that x bar is less than or equal to 63.3, given that mu equals 67.8 is 0.0005, right? That's what the p-value is. That's not very likely, okay? What it tells us is that it's probably wrong to assume that mu equals 67.8, which is exactly why we rejected the null hypothesis up here, okay? Because if the mean really was 67.8, then we shouldn't be observing something so strange comparatively, right? And yet we did observe this, right? We did observe this. And therefore, that tells us that the mean is probably not 67.8. We reject that assumption. Okay. All right. So there's a statistically significant difference here. Is it a practically significant difference? Well, to answer that question, we could construct a 99% confidence interval to get an idea of how much time TikTok users spend watching television. Okay. So we're going to do this using Art of Stat. Again, we're going to enter the same sample mean that we did before, 63.3, same sample standard deviation, 16.5, same sample size, 150. And we want a 99% confidence interval. So let's see what we get. So our sample size we said was 150. Sample mean was 63.3. Sample standard deviation was 16.5. And we want a 99% confidence interval. So I'm going to move this slider over to 99%. Okay, so the average time watching television is somewhere between 59.78 and 66.82. 59.78 and 66.82 minutes. So then the follow-up question, would you consider there to be a large difference in the amount of time TikTok users spend watching TV compared to the general population? Well, in the general population, the average time was 67.8 minutes, right? 67.8 minutes. The TikTok users could spend as much as 66.82 minutes watching television. That just doesn't seem like a very substantial difference, you know. TikTok users may spend as much as 66.82 minutes watching TV. What was it? 67.8. Compared to the 67.8 minutes that non-TikTok users spend watching TV. This is not a substantial difference. right? It could be as much as like an 8-minute difference, or it could be as little as like a 1-minute difference. And even if it were an 8-minute difference, that's still not a lot when you're talking about television. I mean, if they're already spending something like 60 minutes watching television or 70 minutes watching television, then an 8-minute difference really isn't all that substantial. And that's like, at most, it's an 8-minute difference. At least it's like a 1-minute difference, which is just not that substantial. So I would say no. Okay. I think I've got 2 more examples. Yeah, 2 more. So we'll do 2 more. Number 5 here says, according to the MAA, that's the Mathematical Association of America, 1% of bachelor's degrees in the United States are awarded in the fields of mathematics and statistics. A recent mathematics graduate collects a simple random sample of 12,317 recent college grads and finds that 131 graduates majored in math or statistics. Does this evidence indicate that the percentage of bachelor's degrees awarded in the fields of math and statistics is actually greater than 1%? Okay, well, let's see. The null hypothesis is that the proportion is the same as was claimed by the MAA, right? That P equals 1%. The alternative is that P is greater than 1%. The sample evidence that we have in favor of this, in favor of the alternative hypothesis, is that 131 out of 12,317 graduates were math and science graduates. So let's see, 131 out of 12,317 is approximately 0.011. So it's like 1.1%. Now, that does, right off the bat, I'm going to say this does not seem like a substantial difference. However, our sample size is so large that we will probably reject the null hypothesis here. So let's make sure, let's see if my intuition is correct on this matter. We'll compute the p-value by going to art of stat. We'll enter 131 for the number of successes and 12,317 for the number of trials, and let's see what the p-value is. I could be wrong. Maybe the p-value is not so large, or not so small. I need to go to this. Okay. Number of successes we said was 131. Or sorry, this should be our sample size, 12,317. Number of successes was 131. And we don't want a confidence interval just yet. We want a hypothesis test. The null hypothesis said that P should be equal to 0.01, right? 1%. And we didn't want a two-sided test. We wanted a right-tailed test. Okay, well, so I was wrong. Our sample size is large, but this is just not enough of a difference really for yeah, this is just not a large enough difference. So we get 0.2391 for our p-value. So 0.2391. So our decision, we compare the p-value to alpha. Alpha in this case is 0.05. 0.05. Well, 0.2391 is not less than 0.05. So we do not reject the null hypothesis. So then, in conclusion, we would say there is not sufficient evidence, right? We're not rejecting the null hypothesis, so there's not sufficient evidence to support the alternative. So there's not sufficient evidence to conclude that more than 1% of college grads are math and statistics majors. Right? Even though our sample proportion was a little bit more than 1%, it's just not enough of a difference. Okay? Part B asks the same follow-up question as on the previous example, right? What does the p-value mean in this situation? You should pause the video and see if you can write down an interpretation of the p-value, but I'll give you mine. So if we assume that the true population proportion of math and science graduates is 1%, then the probability that we would get a sample proportion of 1.1% is like 23.91%. In other words, there's a 0.2391 chance of us observing this if this is true. That's a pretty large chance. So it doesn't really cast any doubt at all on the null hypothesis, so we don't reject it, okay? Assuming that p equals 0.01, the probability of obtaining a sample proportion of 0.011 or more is 0.2391. In math symbols, you could say the probability that p hat is greater than or equal to 0.011, given that p equals 0.01, is approximately 0.2391. So there's a pretty good chance that we would observe what we observed in our sample if we assume that the null hypothesis is true. And so we don't have any reason to doubt the null hypothesis, so we do not reject it. Okay, part C says to construct a 95% confidence interval for the percentage of bachelor's degrees awarded in the fields of math and statistics. Okay. Okay, so this is our confidence interval, right? Instead of doing a significance test, we need to do a confidence interval. And our 95% confidence interval is somewhere between 0.0088 and 0.0124. 0.0088 and 0.0124. 0.0088 and 0.0124. We got this by going to Art of Stat, putting in 131 successes out of 12,317 observations, and this is a 95% confidence interval. Okay, so there's our confidence interval. Do you think that this is a big practical difference from the 1% reported by the MAA? This is not a big difference. In fact, notice that 1% is in the interval, right? 1%, 0.01 is between these numbers. So we could say, in fact, 0.01 is in the confidence interval, which means it's possible that, and likely, that there is no difference at all. Okay. Because again, this confidence interval here is the confidence interval that we're getting for the new data set, and the new data set, the confidence interval for the new data set contains the 1% reported by the MAA. So it's possible that there's just no difference here at all, and there's certainly not a statistically significant difference because our p-value was so large, right? We did not reject the null hypothesis. Okay, so that's that one. Let's look at one more example. Number 6 here says, among individuals who had credit cards in 2022, the mean number of credit cards was 3.5. A small credit union in Tulare County, California felt that its customers have fewer credit cards than that. They looked at a random sample of 5 of their customers and found a mean of 2.5 credit cards with a standard deviation of 1.3 cards. Assume that the number of credit cards is normally distributed. Part A asks, do the results of the credit union survey imply that the mean number of cards held by their customers is less than 3.5? Well, let's see. The null hypothesis is that no, there's no difference. The mean is 3.5, just like it is everywhere else. The alternative is that the mean is less than 3.5, that the credit union is correct. The sample evidence that they have to support their claim is that the sample mean number of cards at their credit union was 2.5, or at least in their sample, right? Okay, that does seem like a pretty large difference to me. That's a difference of 1 credit card per customer on average. That seems pretty large, but there's only one way to know if it's statistically significant, and that's to run the hypothesis test. So we're going to go to art of stat. We'll put in a sample mean of 2.5, a sample standard deviation of 1.3, and this is a random sample of 5 customers, so we'll put in a sample size of 5. That's not a very large sample size, so we might not reject the null hypothesis here, only because this is such a small sample size. Wow, I can't believe that sample size is so small. Let's see what we get. Okay, so here we are, and we want to enter some summary statistics. We will put in the credit cards. We had a sample size of 5, a sample mean of 2.5, a sample standard deviation of 1.3. And we don't want to do a confidence interval. We want to do a significance test. The null hypothesis in our case was that mu equals 3.5. And we wanted to run a left-tailed test, so we'll make this less. Okay, once again, my intuition was off because we have a large p-value, although this p-value is smaller than in the previous case, but we have a p-value of 0.0803. Okay. Well, 0.0803 is not less than 0.05, so we do not reject. we're not rejecting the null hypothesis. That means we don't have sufficient evidence to support the alternative. There is not sufficient evidence to conclude that the mean number of cards held by this credit union's customers is less than 3.5. Okay. Part B says to construct a 95% confidence interval for the number of credit cards per individual for this credit union. Okay. Okay, so we just want to change the significance test to a confidence interval. And there it is, right? So our 95% confidence interval, somewhere between 0.8858 and 4.114. So we went to Art of Stat. We entered a sample mean of 2.5, a sample standard deviation of 1.3, a sample size of 5, and then we got our 95% confidence interval, and it was 0.8858 to 4.1142. We weren't asked to interpret this or anything, so we're done with that. That's the end of that. But here's what I would say about this example. Our p-value is actually surprisingly small given how small our sample size is. In other words, even though we only had a few individuals in our sample size, the difference between what we observed and what we expected to observe is so large that that we still ended up with a small p-value despite not having very much evidence. Okay. What this tells me is that if this bank manager just increased their sample size a little bit, they would have an even better p-value. They would have a smaller p-value. Assuming that they were able to still get a sample mean of 2.5, if they had this with a sample size of 10 instead of a sample size of 5, they would almost certainly be rejecting the null hypothesis here. So in this case, I think the reason we're not rejecting the null hypothesis is only because of a sample size issue. So we've seen some examples at this point where we had a result on example 3 that was statistically significant and that was practically significant. On number 4, we had a result that was statistically significant, but not really all that practically significant. On number 5, we had a result that was not even statistically significant, and that's probably just because there really isn't much of a difference, okay, between what the MAA claims and what this recent college grad found. And then finally on number 6, we had a result that wasn't statistically significant, but that's probably just because of a sample size issue, right? A larger sample size, and they would probably be rejecting the null hypothesis. So anything can happen, and the name of the game for us is to correctly interpret the results, right? We can compute these results, and we want to be able to correctly interpret them. What I would like to do for these last 2 pages is to just quickly give you an idea of what the calculators over at Art of Stat statistically.com are doing behind the scenes when they're trying to compute a confidence interval. So what the computer is doing when it's computing a confidence interval is it's taking our point estimate, the sample proportion or the sample mean, depending on what it is that we're estimating, and it's adding and subtracting some kind of margin of error, okay? For example, suppose that a confidence interval for the proportion of unicorns with rainbow mane is 0.23 plus or minus 0.04. We're asked to give the confidence interval in interval notation and then describe what's the point estimate, what's the margin of error, what's the width of the interval. Okay. Well, the confidence interval in interval notation would be 0.23 minus 0.04 and then 0.23 plus 0.04, okay? Which would equal 0.23 minus 0.04 would be 0.019, and 0.23 plus 0.04 would be 0.27. Okay, so that would be our confidence interval. The point estimate, right, so this is our CI, our confidence interval. The point estimate P hat in this case would be the 0.23. The margin of error which I'll call E, is this part of the formula, 0.04. And the width of the interval is twice the margin of error. Right? 0.08. So that's the width of the interval. And you can see that here as well, right? The difference between 0.27 and 0.19 is 0.08. Okay, let's do another one, this one with a mean. Suppose that a confidence interval for the length of unicorn tails is 94.7 plus or minus 12.1 centimeters. Give the interval in interval notation, give the point estimate, margin of error, and width of the interval. Okay, so the confidence interval is going to be 94.7 minus 12.1 to 94.7 plus 12.1. And let's see what we get. So 94.7 minus 12.1 is 82.6. 94.7 plus 12.1 is 106.8. Okay, so there's the confidence interval for the mean. The point estimate. Since we're estimating the mean here, the point estimate would be the sample mean x bar, which is this first number, 94.7. The margin of error, we've got some epic music playing in the background. The margin of error, E, would be 12.1. That's that number right there. And the width of the interval is twice the margin of error, right? 2 times 12.1, which is 24. It's 24.2. And again, you can see the difference between 106.8 and 82.6 is 24.2. Okay. Okay, so this is what the computer is doing. It's calculating the point estimate. It's using the information that you put into it to calculate the point estimate, and then to calculate some kind of margin of error, and then it subtracts and adds the margin of error to that point estimate to get us our final answer, our final interval. Well, so then the question would be, how does it compute the margin of error? We know how it computes the sample proportion, we know how it computes the sample mean, but how does it compute the margin of error? How do we determine the margin of error necessary for us to be as certain as we wish to be? In other words, if I want to be 95% sure that my confidence interval contains the population parameter, how big does the margin of error need to be? And so I'm going to give you the result and give you kind of a sketch of the proof. So the result is this. The margin of error that we would use to estimate a proportion is z sub alpha over 2 times sigma sub p hat. All right, our point estimate would be p hat, and the margin of error would be z sub alpha over 2 times sigma sub p hat. Sigma sub p hat we already know, right? It's the square root of pq over n. Z sub alpha over 2 is the z-score whose area to the right is alpha over 2. And we can use technology to figure out that number. We're not going to do it, okay? Because if we were going to use technology to calculate that number, we might as well just use technology to calculate the confidence interval in the first place. But we could use technology to calculate that number. And here's why that number is important, right? The area, the z-score whose area to the right is alpha over 2. So to understand why this is what technology is doing, note that a 1 minus alpha times 100% note that 1 minus alpha times 100% of the observations are going to fall within z sub alpha over 2 standard deviations of the mean. Okay, here's a picture to kind of show that to you. Okay, we know that 1 minus alpha times 100%. Let's put a number to this, right? Let's say that that we want a 95% confidence interval. Okay. If we can find the z-score such that the area to the right is alpha over 2, in other words, if we can find this z-score right here, then we know that alpha over 2, or in this, we put a number to it, or we said 95%. So we know that 2.5% of the observations are above that value, and 2.5% of the observations are below that value, which means 5% of the observations are in the tails, and the other 95% of the observations would be in the center. Okay? This is true regardless of our choice of alpha. Okay? So it's always going to be the case that if we can find this z sub alpha over 2 marker, then alpha percent, or 1 minus alpha times 100% of the values are going to be between those markers. Anyway, the rest of it is just some algebra, but that's the idea. Okay, so this is what the calculators at Art of Stat are doing to calculate our confidence intervals, and this, in a nutshell, is why. We get a similar result for computing confidence intervals for the mean. You don't need to know any of this. I just like to give you the reasoning behind, what the calculators are doing behind the scenes. And that's that will do it for this very long section. Thanks for hanging in there.